Hello and welcome to the winter edition of the CNCF meetup here in Timisoara. My name is Nashon Asari. We have a really packed schedule for you today. I'd like to give a quick intro on the CNCF and what can you expect from the presentations. So first and foremost, for anyone who isn't aware about the CNCF, the Cloud Native Computing Foundation, was founded back in 2015 around the first 1.0 release of Kubernetes, and its main role is to offer governance and guidance to so-called cloud native projects. These are the projects you probably interact with on a daily basis at your job. Things like Kubernetes, etcd, Helm, Containerd, and a lot more. All of these are within the umbrella of the CNCF Foundation. In fact, there's currently 237 individual projects which are part of this. The numbers in brackets are the changes from the last edition we did in September. I would like to mention most notably, I think this is the first CNCF intro I'm holding where we actually have some graduated projects. Knative is an open source serverless solution. Crossplane is a control plane. Dragonfly is like a peer-to-peer data sharing thing. All of these just graduated. And we also had 5 new projects join the fray. If you're interested in seeing all of the projects in a nice interactive manner, you can go to landscape.cncf.io and check it out for yourself. Now, in terms of the local Timisoara chapter, we're 9 people. Most of us are here. We're generally friendly, so feel free to talk to us. Our goal is to bring you all together and talk about cloud-native solutions. We aim to have at least 4 physical meetups every year, so 1 per season. And if you at any stage would like to hold a presentation yourself or sponsor it or host it or anything of that nature, please reach out to any of us. Or you can also reach out to us on LinkedIn directly. We are the ones which are reading those messages. This is also the first edition we're doing live on YouTube right now, which is partially the reason why I'm holding this in English. Thanks to all you folks who subscribed. We can actually stream on YouTube now. We appreciate that a lot. Thank you very much. If for future events you can't make it physically, watch out for our live on our YouTube. I would also like to quickly mention the upcoming May 2026 Cloud Native Days in Bucharest. If you're someone who's interested in holding a presentation there, they open the call for speakers. It's up until February, including, if I remember correctly. So you have a good couple of months to submit your talks there if you're interested. Too much, sorry. Big thank you for today's sponsors and host, Haufe Group, most notably Luci and everyone here. Thank you very much for having us. An even bigger thank you to today's speakers. First, there's going to be Alessandro Pilotti, CEO of Cloud-Based Solutions. He's going to be talking about using Kubernetes to accelerate bioinformatics AI workloads. And then we'll have Rareș Istoc from Cube right here, who's going to be talking about how MLOps is the new DevOps. If you'd like to stay in touch, probably the best place to do so is on our LinkedIn account. Hit a follow on LinkedIn. That's where we post upcoming events most regularly. We also have a dedicated CNCF page if you're interested in joining off the CNCF platform. That is also an option. And with that, I'm going to pass it off to Alessandro to talk about.
Thanks, Nacho.
Floor is yours.
Thank you. A couple of things to set up and then I'll put it.
All right, perfect.
Okay, that should be all set up. Ready? Perfect, yeah. Hello, my name is Alessandro. I'm CEO at Cloud-Based Solutions, company headquartered here in Timisoara. So I'm going to present you some content related to a recent journey that I started a couple of years ago in the bioinformatics world. From the standpoint of a person that worked as a developer, as a DevOps for decades, approximately 30 years of experience in the industry. You might ask, okay, why did you get into bioinformatics? Could you just retire, enjoy your life, or everything? No. I like to do nerdy stuff. I like to learn things, and most important, I needed a way to learn to approach properly AI. So I have a question. How many of you guys are DevOps here? Okay. Any coming from life sciences? Bioinformatics, biology, whatnot? Okay. That one counts here. Okay, good. So one of the main reasons for this was like, at some point, I was trying to figure out AI, a few years ago. Until then, every single innovation in the industry was pretty much a simple progress from the previous generations. If you knew physical servers, you could perfectly understand VMs. If you knew VMs, you could understand the evolution into infrastructure as a service, OpenStack and the likes. If you knew infrastructure as a service bus and whatnot, Kubernetes was a very logical step forward, right? And so on. Then I tried to get into machine learning, deep learning, AI for simplicity, right? And it never really clicked, because in the end, at some point, I figured out that it's not really about the code. Code is just a pretty simple implementation part of machine learning, algorithm, and whatnot. What it's really all about is typically big data and statistics. If you don't have big data, you cannot really do AI, right? You can play with it as much as you want, you will never get anything out of it, right? And if you don't know statistics, you will not be able to understand what you're really doing, right? Coding is still important, right? But it's important in the sense that you need then to put together all these things, understand, of course, all these complex models work, think about transformers and so on, but you won't go far without the first. So I needed a place with data. Data available to the public, not walled behind some organizations and so on. Biology is the perfect place for that. On top of that, I always had a particular pinch, if you want, for molecular biology, DNA and stuff like that, because I always thought about it as nature's way of coding, right? Instead, if you've been a coder for like as many years as I've been, you get very interested in all these sorts of things. So I decided to enroll, so to go back to academia. I come again from a computer science background, right? So I had a master many years ago. And I decided to go back and study in London, in this case, at Birkbeck and UCL, for a Master of Research, okay? Which is something in between a Master of Science and a PhD, right? Because in the end, that's another interesting thing. In the world of computer science, somehow we always kept academia at bay, On one side, you can think about the old, Linus Torvalds versus Tannenbaum Flame, all the way in which we computer guys always rejected the idea of the highly structured way in which academia does things, right? For this type of work, for AI in general, academia becomes again the main source of truth. I saw many people going actually back to look at AI algorithms back on archive, so basically scientific papers, something we never did before. So very interestingly, there is a convergence at this point back between the computer programming world, where we are coming from, and academia again. So I will start with, so my purpose of this, the main purpose of this session here is to present you what I did in terms of AI and how I did pipelines to make this work, right? In order to get there, I have to give you a little bit of an intro about what I'm going to talk about, what the problem is, right? And this is going to be Molecular Biology 101 for DevOps. But you all know about DNA, right? DNA, it's basically nature's source code, right? That's what it is. It's just pure, simple source code, right? It's not written in C++, it's not written in Java, it's not written in Golang, Python, and whatnot. It's written like this. It's not binary. Instead of 0 and 1s, you have a quaternary code made out of 4 possible values, which called bases in DNA, which are adenine, cytosine, threonine, and guanine. Okay, A, C, T, G. Okay, those are binding. So A binds with T, and C binds with G. Okay, they come out in a double strand, right? The famous helix, right? Which is nothing else than the nature's way to handle RAID 1, right? You know what RAID 1 is? Yes. Good, right? RAID 1 is a way in which you have mirroring. So if you lose data on one side, you have a copy. Nature does exactly the same thing. You have 2 copies of the same data, okay? It's not always protecting us, but it protects us for a large number of mutations and so on, not all the time, as we all know, right? But it's also the reason why, for example, DNA-based viruses are very less prone to mutations compared to RNA ones, because RNA is a single-strand, similar type of code. So there are various types of RNAs, but you can think in terms of programming as you start from DNA, and then from there you take some sort of bytecode, like in Java, okay, or in Python, which comes straight out of the coding parts of DNA. There is a sort of compiler, which is the RNA polymerase, which simply goes through one of those DNA strains, copies it, and spits out an RNA strain. So the RNA strain looks exactly like a DNA strain with one single difference. You still have 4 bases, but the threonine gets transformed in uracil. So if you have TGG, you get UGG, okay? Simple as that. Now, we have the source code, we have the bytecode, we need executables, right? So the things that you're actually going to run, the stuff that actually does things, right? Oversimplifying a lot, this can be considered in terms of proteins. Proteins are the cell's executables, right? They're based out of 20 possible instructions. You know, like in computers assembly, you have mov, add, and whatnot. Here I have 20 possible building blocks, each one identified by a letter. The fact that it's identified by a letter will become later, important later when I'm going to talk about AI, okay? You have a particular component called a ribosome. The ribosome takes the mRNA. mRNA stands for messaging RNA, which is the one that contains, if you want, this coding information, and transforms it into proteins, okay? Very interestingly, there is a table that dictates exactly which triplet of bases, RNA bases called codons, are going to translate into one single protein, okay? That table is more or less the same for all living things, and is called, for simplicity, the code of life, okay? But in terms of, from an IT perspective, you can simply think it about a correspondence table between assembler instruction and binary code instruction. It's the same thing, right? To the point that another very interesting similitude is the fact that you're familiar with C type of strings, right? So null-terminated strings. When you have a string in C, you have a bunch of characters, and that string gets terminated with a 0, right? So that's called null-terminated strings. Meaning that when your code is going through those strings, goes through it byte by byte till it gets to a null at the end, right? So it knows that the string ends there. Similarly, the ribosome knows that your protein is going to be finished in the moment it hits a so-called stop codon. There are a bunch of them. UAA is one of them. Okay, so it's the same thing conceptually. So, for example, in the example you see there, CAG is a codon, so a triplet of RNA bases, which translates to a Q. Then there's an S, G, A, E. Those are all amino acids which are chained to form a protein. And then there is a stop codon, UAA, which simply says, okay, I'm finished, right? In terms of amino acids, there are plenty of them, as I mentioned before. They're the main ones, okay? Divided in groups. The fact that they are divided in groups is very important because that will determine the structure of these proteins that you're going to generate. And we will see later why this is so important. You can divide it in polar, polar uncharged, hydrophobic, and special cases, right? Polar means that they have a polar charge, positive or negative, meaning that they can attract or not each other, right? Which will determine a lot how the final structure of these proteins will be. Hydrophobic are important because, as the name implies, they repel water, and of course, in a water solution, they will aggregate together, making typically the big bulk of the core of larger proteins, and so on. Even changing a single one of these amino acids in a protein sequence can lead to very dramatic differences, right? Think about the sickle cell anemia. There is one single amino acid which changes there and changes the hemoglobin protein inside of your red blood cells, right? From a nice disc shape to a sickle, right? Like think about like a moon, right? A gaseous moon. Just by changing basically a glutamine into a valine, right? Glutamine is charged, the other one is not. It's enough to make the protein change completely shape with dramatic results, of course, for the host, right? But just to give an example. All right, my talk is largely based on antibodies, okay? Antibodies, for simplicity, are just big proteins, okay? Which have some very particular characteristics. They have two copies, also called heavy and light chains. A chain, like, is a sequence again of amino acids, right? Variable and heavy parts, in which the variable parts is the one that really interests us because it's the one that gets specialized for specific antigens, right? Think about virus, bacteria, and whatnot, right? It's relatively short, 110 to 133 amino acids, divided in 7 regions, as we will see later. The antibodies, as I mentioned, bind with an antigen. The part of the antibody that binds with the antigen is called the paratope, okay? Epitope and paratope, sorry. I'm not entering into details about how those antibodies are formed and everything, but in all of us, they're extremely important instruments as part of the immune system that will allow us to fight diseases, right? And foreign bodies that enter our body. Unfortunately, also other things sometimes, but let's say for simplicity, let's take that. Right. That's enough with biology. Go back to computers. Transformers. How many of you know about transformers? Yeah, I expect pretty much everybody, right? It's impossible not to these days. You know, when you go to every big IT conference these days, you get a lot of demos about transformers and everything. What I don't really like is that those are typically large marketing-related sessions, very often, where they just take one of those large LLMs, you know, large language models, which are largely implemented with transformers, and you know, you're just running on these very massive models, huge models, right? And a lot of the work in AI these days consists largely in prompting and working with those models, you know, just as a user, and do something with the output we generated from there. This is not something that really interested me. What I wanted was actually building my own models, or at least fine-tuning existing ones on my own hardware without having to deal with large infrastructure, right? Because that is the way in which you can really learn about AI, you know, by going down and understanding how all these models work, how the algorithms work, and everything, right? You cannot really do that by just prompting stuff on ChatGPT, just to give an example. So in our case, we are building transformers, but we are not using the ones that you're commonly using with natural language processing, NLP, meaning that we're not going to ask, hey, give me an antibody that does this and that, right? We are, on the contrary, using still a similar approach in the sense that we are providing strings of data to feed, you know, these models, both for fine-tuning, training, and for inference, of course. But we are, instead of sequences of text, of human readable text, we are feeding sequences of amino acids, so the proteins we were talking about before. So, and another important thing is that when we talk about how we pass this data to these models, we talk about tokenization. So we need a tokenizer that will take these things and split them in pieces that are going to be fed to the models. In natural language models, there are algorithms like WORPs, which are taken, for example, like antibodies are interesting proteins and split them in a list which have antibodies are interesting proteins and adult, okay? That's one way of splitting them. Other ways might split, words apart and whatnot, right? But this is a simple one. In the case of our proteins, it's much easier because we are just taking one token per amino acid. As simple as that, right? Plus, optionally, some separators when we have multiple separate chains, right? Of individual polypeptides and so on. What we're going to have here are a bunch of models. So this was part of my research here. So taking a bunch of models existing in the industry and compare them to see how they performed on some biologically relevant problems. Again, we are not using DeepSeek or OpenAI or Claude or whatnot here. We're using models which are specific for the domain. It's an example, of course, in biology, but you could, extend it to any other domain in which you have, at this point, models which are specialized pretty much for everything out there. Right? We have two categories of models here. One is called protein language models, PLM. Unfortunately, who did this was not Romanian, right? Okay. So I will try to remember to spell it all this PLM very clearly, right? Trained on generic proteins. Very large models, some of them, ESM1 and ESM2, are actually coming from Meta, right? So from the scientific group in Meta. And they are massive models, trained on thousands of GPUs and everything, right? So, of course, not this type of thing that you could train on your normal infrastructure, right? But you can perfectly fine-tune those models with a relatively affordable type of infrastructure. Then we have a group of models which are much more specialized, which are trained only on antibodies. Again, antibodies are a subset of proteins, right? But they have they're highly specialized in what they do, meaning also that the training will make sure that the models can learn something which is very specific to that, instead of all sorts of protein features that proteins might have, which is huge. And here I have a list of one: Antibert, Antibert2, ABLM2, BALM, and DSM. Not entering too much into the details, right? All these models are largely based on top of the BERT architecture, which was the very early ones to emerge on top of the original transformer paper. So that paper came out in 2017, I believe. It's called "Attention is All You Need." That's the thing that basically changed our life, if you want. Good. Again, I have the models. I have the data, as you will see soon. I need some use cases. So we have two particular use cases here. One is called antigen specificity, that given an antibody, it will tell you how well it's going to bind to a given antigen. This is a binary classification problem, meaning we have two labels, yes and no. So it's a relatively straightforward and easy problem. Of course, antigen specificity, like everything or most things in nature, is not strictly binary. So it's not that an antibody binds or doesn't bind. It goes on a spectrum, right? But you can just put a threshold and say, okay, under here it doesn't bind, beyond this it binds, okay? For simplicity. And that has a lot of use cases. Well, we're going to use SARS-CoV-2 spike protein databases here. You're all familiar, or at least your body most probably is, with SARS-CoV-2 spike proteins, right? Because we had a lot of fun with them a couple of years ago. On top of that, if another pandemic happens, I will be able to say I did my own research. Yeah, those things are very highly available in the sense that there are a lot of data sets out there which contain this type of sequences. So they're perfect use cases, right? Some reasons why you might want to study this is that you might want to know whether a given antibody, which you know is binding to a given variant, is going to be able to bind to a given mutation. Because as I mentioned before, you change a single amino acid in the sequence, and you might change dramatically the properties of that particular protein, including, for example, the spike protein of the SARS-CoV-2 virus that will at that point not be able to be cooked into, into an antibody, like a specific antibody for that. Not entering too much into the details, right? And that's one of the two use cases. The second one is paratop prediction, that given an antibody sequence, it's useful to know which positions belong to the paratop. The paratop, as I mentioned before, is the interface of the antibody, which is actually binding with the epitope, okay, with the part of the antigen which connects to the antibody. You can see them like a sort of Lego pieces. You see them antibody on one side, the antigen on one side, and you want simply to lock it in somehow, right? And neutralize. That's pretty much how nature works. Good. This is a token classification problem, meaning that you don't have a single label for the whole sequence, but you have a label for each individual token there, right? So you want to know yes or not, right? And that has a lot of applications potentially, of course, in the biological space. Now, fine-tuning models. Fine-tuning is the most interesting thing here, because you're going to take a model, very often trained on something else, and you're going to feed it more data with labels, and you say, okay, take this data and try to learn out of this some information that I will need during prediction later, right? We could take all those models I mentioned before and use them as they are to run prediction with the problems I mentioned, but we will have most probably very random results because those models are not trained for this. In order to do fine-tuning, we need 3 data sets: training, evaluation, testing. Right? I will have a slide a little bit later. Who knows about data leakage here? Good. So the very important thing you want to do when you train a model is to make sure that the model doesn't already know the answers when you test it, right? So you want to keep those data sets completely different. It's like somebody studying in school. You don't want to give them the tests while they're training, while they're learning, right? Because otherwise they can learn it by heart and simply be a parrot and say, oh, I already saw this thing, right? Unfortunately, that's not how it works these days very often in many universities, but that's a different story. But when training your models, you absolutely want to avoid this train-test contamination we will see very soon. So completely separated. And then ideally, you want to have a separate part of the data set for evaluation, meaning that during training or fine-tuning, you're constantly iterating on the data, in splitting your data in 2 groups, one for training and one for evaluation, right? You evaluate performance, right? And then you take the best one that you get, right? Those are continuous iterative cycles into so-called epochs that you do for your models. How do you divide this data set? Well, there are various methodologies. I use a thing called stratified k-fold cross-validation, which I don't have the time to go out into, but it's one of the many ways that we handle it. Another thing you want to take into account is so-called hyperparameter optimizations. When you train those models, those transformers, you have a lot of different options on how to do it that will determine the output. For the batch size, or for example, how many samples at once do you feed to the model, determines very often the performance. And that is also limited by the type of resource that you have, right? Because all these things very often tend to work at the capacity of what you have, and they might be relatively limited. So you have to optimize in function of the hardware that you have and in function of the resources that you want. Number of epochs, learning rate, and so on. Another important one is that when you fine-tune a model, This model had a lot of layers. If you don't freeze a part of those layers, you end up simply wiping out all the knowledge this model has. So it's a very primitive approach that we have these days. There are much better ones. But as a basic, you're just simply freezing a bunch of layers, typically the bottom, a given number of the bottom ones, right? Meaning that those layers will retain the information that was already pre-existing during the original training. For example, you have, I don't know, 16 layers. You freeze all the first 13 and you keep only the last 3 as a variable, meaning that those are the ones that are going to be affected by your fine-tuning. So playing with the number of layers that you need is also very important. It will lead to different results. Those are called, again, hyperparameters. Then you have other problems in fine-tuning, which are, again, strictly related to the hardware you have. Some models, like, for example, the ESM2 with 15 billion parameters that we're going to use, don't really fit in a single H100 very often without doing some tricks. I use, by the way, 2 H100s, 2 NVIDIA H100s for all this work here, which is actually the same hardware you will use for the demo in a bit. So you might also do small tricks, like instead of using 32-bit floating point numbers, you scale down to 16, right? So you basically halving the amount of space you need. You might limit the batch size, use accelerators. I will talk quite a bit about later. That will improve, let's say, how the algorithms work on your hardware. Now we go to data leakage. So partitioning properly data set is critical to evaluate a model's performance. You don't want to have train test contamination, right? It's extremely common. And it might be a relatively simple thing to think about, because I say, okay, I make sure I compare all the strings. I make sure that I don't have the same strings in the 2 data sets. That will make my 2 data sets completely separate. But no, that's not the case, because information might leak beyond simple strings, which is our case here. In our case, for example, when you think about protein sequences, right, they might not be perfectly aligned one to the other, because, for example, in one sample, one might be missing. In another one, it didn't come out from crystallography, just for an example, right? So you have the same data, just shifted by 1 byte. No? So if you compare the strings, you will say, well, those are 2 different strings. But if you use some more complex tools that will compare those sequences, like knowing the biology behind it, it will tell you, well, these 2 strings have, for example, a 90% similarity, right? So by using a process called clustering, we simply wipe out everything which is too similar, right? So you start with a relatively large data set, and you'll end up with smaller and smaller ones when you do this, right? So it's very important, because on one side, the less data you have, the more overfitting problems you might have later. But on the other side, if you don't do it, you get garbage, right? Garbage in, garbage out. So very often, as data scientists, we might want to take shortcuts, but if you take it, you end up with garbage data, no matter how good it looks. This is a big problem in science these days, right? Especially publications. But it affects also the industry. Good. Now, all this work I presented results in around 600 individual tasks, okay? So if you start running them manually 1 by 1, well, it's not going to end well. Also because you want to have something which is perfectly repeatable. You run it twice, you get the same results. This is very difficult when human error can already add that, right? And you do it all the time. You change one sequence in the source data, you have to rerun the whole pipeline, right? And also, you don't want to stay there and wait. You want to run it, go to sleep, wake up in the morning, get a coffee, watch the results, right? So this is very important. Okay, most of the tasks require GPUs. That's a given, right? More on that later. Tasks are connected in a directed acyclic graph, DAG. Ever heard of DAGs? Do you like DAGs? Right? Support from so that's a nice way to put tasks in a sequence or executed in parallel when they don't have any dependency among each other. Apache Airflow, it's a very common program for that, right? Dagger, it's a common one in the CNCF space, but it's much more dedicated if you want to CI/CD. Nextflow, it's one that emerged, in particular, as a sort of de facto standard in biology, but there are many more, right? What you want is any of those workflow managers that will simply be able to sequentialize tasks, right? The demo I'm going to show is based on Airflow. And then you need something underneath that will render the HPC side of things, the high-performance computing part. And traditionally, that's the world belonging to software like Slurm, SGE, Singularity. I don't know if you guys heard of those, right? Singularity changed name also recently. Kubernetes is getting more and more and more into that space, because while Kubernetes was not born specifically for that, right? It still works, if you want, perfectly well, because in the end you just need something that schedules and runs job, right? Kubernetes doesn't provide natively, if you want, all of the scheduling ability that we need for these jobs, right? But then you have something on top like Airflow or Nextflow and everything that will do the work for you, right? Kubeflow, of course, right? Why didn't I use Kubeflow? Because I wanted my software to be able to work also not only on Kubernetes, but also on Slurm, SG, and whatnot. But Kubeflow, for example, is the de facto, if you want, native approach for it. Here is how the whole pipeline looks like, simplified view. In yellow, you see the tasks that require a GPU. And yeah, in general, you start with the data set. So that's common work that has to start before working on the models. So you start with a cluster training, splitting, training validation, undersampling if you need it, shuffling because you want to have also separate control in which you simply shuffle labels to make sure that the output is fully random, right? And so on. Once that is ready, and you need to do it anytime you change even a single sequence in your input, right? You have to start all the bulk of all the GPU operations, which consists, if you follow the arrows, fine-tuning, fetching attention weights, prediction, and so on. And when all the stuff is ready, it generates some artifacts, on top of which you run some reports, which in my case I've written in R. R is another language that I learned for this purpose, which is very common in statistics and actually much easier than Python and similar when it comes to actually crunching data just for visualization purposes, right? When all this is done, it sends an email, okay? This is the Pareto prediction pipeline, which is even more complicated than the other one, because it has to do all this fine-tuning and predictions for each of the regions inside of antibodies. Just for simplicity, antibody have 7 regions divided in framework regions and CDRs. CDRs, complementary determining regions, are the ones which are actually attaching to the antigen, right? So you want to see how the model performs differently based on that. Because, for example, in the case of Pareto, the core of the antibody will have 0 Pareto members. So your data will be completely skewed in terms of balancing of the classes, right? While the CDR regions, on the contrary, will be the ones facing the antigen, and there you have a given balance between non-binding and binding, right? So if you look at the results of the performance data will be completely skewed between them, right? You might have a wonderful accuracy on the framework regions just because they're all zeros, right? But it doesn't mean that your model is working well. So you need to separate them and one by one analyze the data separately. Okay. On top of that, we need to run some specific software for the industry that, for example, given a sequence, will automatically number the antibody and standardize them, because antibody again have standard numbers, right? So you say, okay, this is part of the framework region, this is part of the CDR, 1, 2, 3, and so on. All those things have to be executed one after the other. I'm going to show you already a demo before going to the rest of the stuff here. So what you see here is the interface to my Airflow instance, which is running on top of Kubernetes cluster, running on top of a server with 2 H100s, which is sitting right now in the cloud-based offices here in Timisoara, right? So I'm VPNing there. If you look here on the left, you have all the tasks, which get nicely grouped. For example, Git. Now, at the beginning, you do a Git pull, a Git fetch, and you basically check out the latest commit, so that anytime you're running always on the latest version of your software. So every single task will be guaranteed to use always the same and latest code. And then you have, for example, here the sequence of what you need and everything. Then you have the reports at the end, and so on. Like, and then if I keep on exploding here, filter data, and again what it is. And here I have the individual task being executed. Okay. The VPN just gave up. Now, without further ado, I'm going to start this pipeline. The way I built it, since it takes, again, a lot of hundreds of tasks and hours to complete, even on powerful hardware, you don't want to have to rerun everything when you change a single detail, for example, in one of the models. So the whole thing is spread in a way for which each task has a, do I have to run it, and run it, right? So each task, the first part simply checks make file style if the artifacts generated by the particular task are more recent than the input data. If the input data is more recent, it means that you have to run them. It's like make will run in a compiler, right? For a compiler case. So now what happens here is that this thing is going task by task, all of them, saying, do I have to run them? And then sequentializing them. Pink one means skipped, I don't have to run them. Light green means I'm about to run them or I'm running them. And dark green means it worked. So if I go here, you guys familiar with KNS? Good. So now you can see there is a predict anti-Bertha2 age FT. So that tells me it's like prediction on the anti-Bertha2 model. Fine-tuning and age is because I'm doing all the age chain, right? I mentioned before there are heavy and light chain. This is the heavy chain. And if I look at it, I see all my typical PyTorch related stuff. Now, this is usually all, I'm using Hugging Face and PyTorch, by the way, for most of the stuff, right? And if I go back here, even this one, I can basically split it in all the bits and pieces and see the various tasks going, right? Actually, yeah, it's already finished. That was so fast. Good. So let's take it, for example, here. Logs. So here, oh, I have the same logs that you see over there. I see them here, right? Yeah, this is the same stuff that you could see in the output of the container, right? You can see. So this is very nice and simple way to debug this type of information.
Question: what was the failures?
In general, or?
Yeah, in general.
Well, there are gazillion reasons for failures. Could be issues with the models, issues with the code, and very often issues with the amount of free memory you have, right? I will get later on that and why it can fail very often. Of course, there is also resilience in build still, meaning that when something fails, it will retry multiple times, right? Getting there in a bit, actually, because it's a very important topic that you're raising. When all this stuff is done, I still have a bunch of containers running. So now new containers start because I will have to start, you see RMD, it's an R process, so I'm running statistic now. So I'm taking all this massive amount of data I have, and I am basically making some plots that I will send by email when it's done. Almost there. While we wait for that to happen, I keep on going with the slides. Let's keep this part an open stack. Storage considerations. You need a read-write many CSI because all the pods need to share the same data underneath. Okay. Two examples: CephFS, recommended for production use cases. You just have a Ceph cluster underneath. CephFS does fantastically, right? Best thing ever. For a POC like this one, or situations in which high availability might be that critical, you go with NFS. Also very, very easy to set up. Both of them support read-write many. So basically, you create a single PV, a PVC, and you expose that to all your pods, which get automatically created. If you run on hyperscalers, you can also evaluate other options like Azure File if you're running Azure and so on. Now, getting on what can cause failures, and towards the end of my session here. Those GPUs are expensive. Not only they're expensive, but you can stay there like, shut up and take my money, right, for a while to get from the time you order them until you get them, right? As you probably know, they're very hot commodities. So you want to use as much as you can out of them, right? And you have a various way of doing it with NVIDIA. This is, of course, NVIDIA specific. You have MIG, ideal for OpenStack related or other virtualization stacks, in which you separate, basically split in partitions those GPUs, and then you expose them to the VMs, which could be, for example, your working nodes in Kubernetes, right? And then those are exposed to the workloads. Time slicing, the easiest thing, what I'm using right now here, is brutally simply shared between all the tasks which are using them, right? And all those tasks are going to compete and scheduled on top of that, right? Then you have multi-process service, MPS, which reduces the overhead compared to knife slices, especially with a lot of small tasks. Improves a bit time slicing isolation compared to time slices, because again, MIG gives you full isolation, meaning you can have two independent customers running it. And then you have time slicing, which means all of them are sharing, meaning that if you have a bad actor in that code, that actor will have access to whatever else on the GPU, right? So if you are the only one using them, that's good. If not, it's a problem. MPS is kind of like an in-between thing. Right? In terms of optimizations, models tend to be very greedy and then to use a lot of your resource, of your memory there. You want to make sure that you are reducing as much as possible the memory they use. And second thing, if the model needs to stay on more than one GPU to scale, right, you need to find solutions to scale that model across that. Like, for example, NVIDIA has a thing called NVLink, which allows you basically to group GPUs together without getting too much details. One thing I like a lot is Deep Speed, which has a set of algorithms called Zero Redundancy Optimizer, Zero. How many of you ever heard about Zero or Deep Speed? Good. It's one thing that you can enable it very easily and changes your life in terms of how well your models perform, right? So it's highly recommended. Zero has 3 variant options, 0, 1, 2, 3, in which you have look at the sharded optimizer, meaning how all this data weights and everything are divided in across your GPUs, gradients, parameters of the models, and of course, very simple indicators about the memory savings. Stage 3 is the best one in terms of memory savings. Communication cost, meaning that communication across GPUs, right, from low to high. And in terms of setup, how complex it can be done. Use cases, for basic models, just go with 1. Big models, you can go with 2. And with very large models, like for example, the 15 billion parameters we use, you can go with 3. Okay, here is where all the code lives. This is all open source, of course. And now back to the demo. Okay, should be pretty much done here. Here it is, everything finished. Now I'm getting an email with the results, okay? I open up here for simplicity the previous one so that you guys can look at it, what it looks like, right? So this is a result of the R script. And it shows me from every single model, so you have models here on the X, right? Antibacterial, antibacterial 2 and everything, ordered by type and size. And you have a precision, specificity, recall, FPR, F1, AP, balanced accuracy, AUC, MCC, and so on, right? I'm not entering into details. Those are all statistical, let's say, instruments that you have to evaluate how well a model works. And there is no simple one-size-fits-all. You cannot say just, I'm using one of those, let's say, accuracy or balanced accuracy, for example, that will work with every model. No, every single model has some specificities in which you have to know the strong points and weaknesses of all these statistical instruments and use the best one for what you need. Otherwise, you end up with results that might sound incredible, but incredible or not. For example, precision. Everything looks dark green here, which means very high in my scale. Doesn't really help me much. Specificity just looks better, like recall and so on. AP looks pretty good, right? AUC are under the rock curve, right? So another thing that people use very often. I don't want to go into details, but just to give you the idea of what you can achieve. It doesn't matter if it's biology, if it's marketing data, if it's, I don't know, whatever else, your models will work pretty much in the same way and will end up needing this type of statistical evaluation again. Here you have an interesting one in which I'm comparing how much the attention, meaning how much the model is basically paying attention, if you want. How likely is one token basically to jump to another one in particular? In the model, I'm trying to oversimplify inside of the sequence, right? And if I take, for example, this anti-beta2 here, it shows me that there is an increase in attention, as we would expect, in the array, which are the dark gray ones, which are the ones which are in contact with the antigen, right? Means that my model actually worked, my training worked, because it signifies that the models became there is more higher probability to predict actually residues, positions which are within that those ranges, right? And I show how it was before, how after, and how it changed compared the fine-tuned before the pre-trained one. So same models, same data, see how the performance changes, right? Similarly, token classification, I'm trying to predict how well these models are going to tell me, yes, those things are part of the antigen or not. And here, for example, this one does pretty well, this anti-beta2. The yellow ones are right predictions, okay? And if those yellow ones, for simplicity again, are inside of those CDR regions that you see on top, right, it means it's doing well. To do it perfectly, it has to nail exactly the right position that the test data is telling me it is, right? So there is work to be done, but we are hitting some work. Especially if you compare it with what happens in the pre-trained case, so with before the fine-tuning, in which everything is largely almost random, right? And it's also interesting how compare, for example, highly specific smaller models, highly optimized for a specific task perform, compared to, for example, the large general ESM2 protein-based ones, which know nothing specific about proteins, about antibodies, except for the fact that inside of the thousands and thousands and thousands of proteins that were used for training them, there are also antibodies, right? In that case, it's quite interesting to notice how the performance increases, starting from the smallest one, 8 million parameters, a very tiny model, okay, which is inexistent in terms of performance, down to 15 billion, which is a massive model, okay, which is here, where you can see it's performing pretty much as well as anti-beta2 is working, right? Where anti-beta2, as I mentioned before, it's highly optimized for antibodies. Right? And again, the pipeline spits out all sorts of metrics for all possible bits and pieces of the antibodies. So you will not be able to do this manually and retain mental sanity, right? So you need a pipeline that does all this work for you, right? So building this pipeline at the moment, if you want, is a bit of where the challenge for our DevOps is, right? Because those will require pretty much all the instruments we know, right? Mixed, of course, with AI, right? You can even consider the AI part as black boxes, but building the pipelines is what we need to learn to do, right? Good. I think I'm pretty much at the end. I am. Questions?
I think you left a very interesting angle at the beginning of the presentation.
Thank you.
What?
Thank you.
Why you started with biology because of the data research, right?
Correct, yeah.
There are some discussions right now that data does not keep up with the infrastructure which is scaling, and also synthetic data does not help. So we cannot go further to smarter and smarter models. And an idea is to embed the training part into the human brain, because there is a lot of data, and there are some discussions also, maybe you know them, that a child like until 8 or 9 years learns how to process much more data than the current state-of-the-art models process through the large corpus of text data, because of the visual data, which is much more bigger. And I'm curious about your perspective into involving the training into the human brain.
So you're exposed to two main problems here. The first one is data not keeping up. It's true. You have two problems here. The first one is that data is getting more and more contaminated. Okay. And the second one is that yes, the technology improves, but all this work that you saw here is made with a few thousands of antibody sequences, all of them taken out in forms of blood, literally, right, from somebody. Plus, of course, in some cases, some monoclonal antibodies, which are, of course, synthetically engineered and everything. And that makes it very hard in the future, even if you get more and more complex ways of processing that data. If you don't have the data, we don't go anywhere, right? So finding better ways to extract data is extremely important. The second part about the human mind and everything, okay, that's about my pay grade, if you want. But we have a cognitive sciences professor here behind. So for later, if you want, you can ask this type of questions. But yes, that's exactly great. People think LLM is the greatest thing in AI. LLM is nothing. LLM is just a thing that we saw worked, and we managed to make it work by training you with enormous amount of data, enormous amount of resources like ChatGPT company are doing. But if we could figure out how biological process like a human brain does it, we will be able to do it in a much more efficient way. That's why many scientists in that space these days are moving away from LLMs, right? From transformers. Transformers, yes, is a tool, but it's not the be end all, right? Just like when you have a hammer, all you see are nails. That's the problem. Okay, good question.
Maybe
They're gonna kill me, I think. You can try.
I can try. Okay. I'm curious, what do you think about the current infrastructure? How we build that from my discussions with my colleagues also. We don't think that we can reach smarter models by the current. We based on math. I don't think this is not enough from our perspective. I'm curious about yours. That we should change from the ground base how we build models, not relying on math, because we are losing information when we want to represent in math the complex world around us.
That is absolutely correct. It's correlated, if you want, to the previous question/answer, right? Yes. So what we're having here were just statistical models, right?
Yes.
They're not bringing us. I mean, as they say, everything, every technology complex enough is undistinguishable from magic, right? They say, if you use ChatGPT, you're just blown away. You're like, how the heck does this model do that? But in the end, if you look how they do it, it's by a relatively between quotes, right? Simple approach with an enormous amount of data, right? But that doesn't mean that it's intelligence, right? Any other questions?
Use a huge amount of tools to build this whole pipeline that we built. And I played a little bit with AI, and I found the documentation a bit lacking, and it was hard to find my way around. What was your experience building this pipeline? Because I see a lot of tools, and like you also have some H-series GPUs, and how was building this stuff? Because like you showed
that's a good question. That's one of the reasons I decided to share as much as possible within computer science communities. Because yes, you go to Hugging Face and you say, great, now I'm going to build a model from scratch. And you spend ages just to try to find your way around that, right? Fine-tune the smallest, simplest task is crazy. And when you go to acceleration, you got into black magic, basically, because, of course, say, a lot of things are simply rewriting and replaces basically classes and whatnot on the fly. So that there is so much stuff that you have to just dig through it to figure it out piece by piece, like the hard way. that, and it's typically is because when you look at a paper, you know, that is just part of the methodology. It's like, okay, yeah, you did it, good, show me the results, you know. But for us, for me, it meant working months and months just to figure out every single of these components. But on the other side, this particular program gave me the reason to start doing that, you know. So that's I think what sets myself apart from my previous self before I started doing biology, which yes, I had all the possible knowledge in computer science, but I was missing the way and the reason to go and dig into all these lots of tools. On top of that, of course, I reused as much as possible things I know: Airflow, Git, DevOps methodologies, CI/CD pipelines, you name it, right? But yes, there is documentation needs to be improved on that space. And again, it's two different worlds: scientists and computer guys, and very often we are looking at different things in documentation. You know? That's why I think there is also a different approach to that. In our case, it's the bio and informatics side of things. But okay, I think the very last one.
Since you started this, how much did the technology in terms of cloud pipelines have evolved since you started this?
That's a great question. So one of the reasons, of course, I delved into these things is that at the company I always did the R&D, right? So I spent all the time, building new projects, trying them, see what sticks on the wall and whatnot. At some point, that pipeline simply dried out. Cloud computing is highly commoditized, got to a point in which it's very mature, meaning also that the rate of innovation in cloud computing is relatively small at this point. Meaning that not much really changed in clouds in the last couple of years, right? Think about even Kubernetes here in the CNCF, right? We deal at this point with very mature type of project, which is a very good thing in my opinion, right? That doesn't mean that those projects are boring. It means that there are tools to be used and innovation has to move somewhere else. So also, just to add on that, my point is like to free myself as much as possible from hyperscalers. I don't borrow really much from Marx, but I believe in the fact that if you don't own the means of productions, you're going to be somebody's slaves at some point. So I really want to make sure that all these models work on premise. This is why I work a lot with Kubernetes, all these things, making the stacks from the ground up, making sure that they work without requiring public clouds, right? Case in point, this one works on a server with Kubernetes running locally, but any on-prem infrastructure will do the same, right? Okay, guys, I think we close here, and for any further questions.
It's all good. So we take a short break, let's say 5 minutes, because we're far behind the schedule, and then we're back with Rareș and why MLOps is the new DevOps, and after that we have a pizza. Okay, quick break. Thank you. Go.
Yeah, cool. Good. Waiting a few moments so everybody can take their seats peacefully. Yeah. That's good. Why everybody is so quiet? Is the funeral or something? No? Okay. Good. Shit, I forgot to introduce myself. Hi, I'm Rareș. By the way, been in the game since I had 14 years. Have played many roles in different companies. Actually, I started my own company 2-3 years ago, which we focus on building end-to-end production AI and ML machine learning systems in production at scale. We are mostly involved in all the end-to-end process of building, training models to building them to shipping them and scale them to production to tens and thousands of users. So basically that's this presentation about is mainly is raising awareness. That's the main thing, because the industry is changing. We are slowly shifting into something new that most people don't necessarily comprehend, and it's scary shit. even for those who have had experience in this stuff. And personally, I have PTSD and I have nightmares because I'm still doing 24/7 shifts, on call support, 3 in the morning if something goes wrong, but not necessarily about classical software, because predictions of ML models and data drifts happen all the time. So first, I forgot. How many students in the room? If you need a job, call me. First of all. Okay. How many DevOps engineers? People heard of MLOps? Nice. People who really do MLOps? Nice. Just a few. Good. Just wanted to check out the room temperature, and because I'm almost gonna shoot myself because I have a lot of emotions, that's why I did this. And also test the experience of everybody, so I should adapt my language to things. Oh, the agenda, right? So the first thing that we're gonna do is I built this so I can accommodate to any audience, because I didn't necessarily know that we are gonna have like students, and I wanted to do something that we will adapt to like any level, and to take you on a really amazing road of how things evolve from way before I was even born, and I didn't got to know all this stuff. Unfortunately, I wish I was born 90s, 80s, but yeah, I blame my parents. Good. So we're gonna start by seeing the dark ages of software delivery, mostly how things got started. We're gonna go to why DevOps was invented in the first place and why it has revolutionized. Then we are going to examine, for the students. I know there are a lot of experts here who already know, but just a short reminder: repetition is, the mother of strong knowledge. So that's what we're going to do here. The pillars of DevOps. Then what happened recently and what everybody's talking on, LinkedIn and stuff. How machine learning, fucked us again. So we need to retake everything and relearn everything, and we need to shift, and we need to make a transition to the new things that are gonna come. The hidden technical depth of machine learning models and what they introduced, in the world of production systems. And then we're gonna go, with our own personal story. 6 years ago, we not 6, 4 or 5. Yeah, we built a startup, which was so dear to us. We shipped cancer treatments. So we analyzed and trained a 2.5-day model on CT scans, which did organ contouring. So everybody knows the system of Romania, and I have a few personal cases and friends who got their parents dead because of ignorance and how people treat patients. So we wanted to make a change and reduce the time of cancer treatment to help people. So I'm gonna tell our story, what we've been through, from building the model in shipping in hospitals with real patients, with real data, with real data drifting and prediction. And then the MLOps movement, a bit of LLM ops. I don't know how many of you know LLM ops. Try it. Okay. And what's next? What the future is going to be? And I think we've analyzed that edge AI models are going to take over in a few years. So we're going to do something about that. Good. So yeah, the dark ages of software delivery. Okay, so previously how software was delivered, people were writing software and features and stuff like that, and usually they packed this and zipped it and shipped it to like a CD, floppy disk, whatever, stick, and wrote some documentation code and throw it over the wall to the operation guys. So there were like two different worlds. There was the development team who focused more on building software, and the operation team who focused on configuration of servers and infrastructure, setting up infrastructure and stuff like that, and monitoring, maintenance, and yeah. Then everybody prayed, and yeah. So after they prayed, and deployment started to have problems, and delays got, and everybody was called in. Some of them may have canceled their vacations and stuff like that. Then after they stood a lot, the blaming game starts. So everybody was throwing shit to each other. Like ops misconfigured it, and dev shipped garbage, and really nobody knew what was the idea. So this segregation was really bad. Things were immature in terms of nothing was stable. There were like Snowflake servers and stuff like that who were pretty bad and unpredictable stuff that happened in the past. So then a few cool guys created the DevOps revolution to address this stuff, because nobody wanted to ship software in 6 months to 1 year. I mean, we lose money, and people needed to be more productive in this sense. So what they did, it was like there was no new technology or no new tool. What they did, nothing fancy of product and stuff. They just built a new methodology of working together. So this proves again that working with people and communicating is the hardest job that you can do. So that's what they did. So one major thing they did, like bring in ownership. So there was no dev and ops team. There was just joint ownership. So if somebody had been called at 2 a.m., everybody was in. So if you fucked up, we fucked up. So we are a team. We're gonna take the shit together. Yeah. So they shared the same goals, maybe some repositories. I don't know. And then they automated everything, because human hand is really unreliable. Things can go wrong. Your girlfriend may dump you, and you may suffer, and you hit the wrong, the wrong click. Stuff like that. You get drunk, the next day you have to deploy in production because it's weekend, and we don't usually do production deploys on Friday, or that's the main idea. And they basically automated everything to CI/CD pipelines, which I'm gonna explain a bit after. Then observability, because really they wanted to know like how CPU, like how much CPU did this consume, how much memory, logs and stuff like that, I/O operations, disk operations, network traffic, bandwidth, almost anything that you can measure when you're delivering software. Small, ship, and often. So basically what this means is don't release code in 3-4 months at the whole time. Just break it and ship it more frequently, progressively. That was the main idea. Yeah. So a lot of new stuff. So CI/CD. Basically, every time you write code, you send it, test it, do some linting, right? Everybody does that, or at least I have the impression that everybody does that. We test it and we integrate it with other folks, so we see that nobody, made any, nobody broke the code, or nobody did any errors, and automated in minutes, not necessarily in months. Infrastructure as a code. So this solved the problems with Snowflake servers. So what they did is, just don't go on, your machine and configure it manually. Like they build tools like Ansible and Terraform and infrastructure as a code tools that can do this in a reliable way, in a static way. So if I want to, I have a production environment, and it breaks, my boss will come to me and will say, how fast can you ship another production environment? Oh shit, man, I don't know. I need to go to the server. I don't know. I just want to go home. I have dinner with wife. We need to do this. So this tool saved us time. Like now in Terraform or Pulumi, or I don't know what you are using to ship environments, I usually start my own production environment in, let's say, half an hour, because databases usually get more to get configured and caches and stuff like that. So in half an hour, I will have a pretty new production environment up and running, just like that. No more manual configuration of servers. Good. So Docker. I still don't get why people don't teach you Docker in universities. Are you mad? I don't know how to say this. Why I talk about history in the first place is usually history, the past help us understand, what we did wrong. And I think most of the people use software without knowing why it exists or why was the purpose of that software, like the need of that software, and understand the history behind that software, why people needed to build that. If you study Rust or Go language, Rust has a really amazing story about an elevator, which blocked, and some guy thought that it has a memory issue. Or, it's true. He lived I think, in Canada, the guy from Firefox. So really, history, teaches us why they needed what they needed. It's like design patterns, right? People teach design patterns just like they were invented, not as they were discovered, because they were discovered, not invented. Because some guy, had a problem, another guy had a problem, another 10 guys had a problem. So they needed to actually create a common reusable pattern, right, to solve that particular problem in time. This was not invented. Nobody stood 10,000 hours in front of a research paper and did nothing, right? Good. So Docker, really, what Docker does in a sense, it's creating, the best definition I found is creating reproducible environments. And what it means by that is, it takes packages, it takes software, it's just, playing around with your operating system and fix some processes behind. And, in the root process of whatever you use, Linux, Windows, whatever. So that was it, shipping codes, shipping packages, and shipping all necessary dependencies in one reproducible way. So that meme with it works on my machine was solved. Nobody talked about that. Well, not necessarily. You may configure things really differently. So I really tell people that, if you use Docker, if it works on my machine, it will work on yours too, and in production and in cloud and everywhere. Yeah, if you configured it right using your orchestrator. If you don't configure that with your orchestrator right, it will blow mostly. So I do that the same. I have the same curse, right? So nobody's perfect. Observability, I already talked with you about observability, logs, metrics, stuff like that, blah, blah. Let's go to, are you interested in numbers? Me neither. At least the problem was solved, and we do more frequent deployments and load time and blah, blah. I do deployments in 5-10 seconds, 2 minutes, 3 minutes if I use caching. So the problem was solved. That was the past. We really do great things right now. Oh, shit. Okay. Good. Now, spicy stuff. Machine learning did it again. not necessarily again, but broke everything. Because there's a big paradigm which is shifting. That stuff is actually true. 87% of the ML projects really remain at, the level of experiments in labs, in a forgotten Jupyter notebook, on a work computer, and nobody touches that anymore. We've seen it. I mean, who deploys, great ML projects in production? IKEA, Uber, Netflix, Amazon, which, our PIB, it's not high that Amazon invests in their teams. So they really know how to do it. Most people, everybody's throwing right now money in initiatives and ML projects and stuff because it's the hype. In a few years, they won't get their investment back. I hope so. So, yeah. So, scary. Why is that? Because machine learning models are not static software. Usually when you ship static software, you package it in a Docker, you ship it, and somebody clicks on it, and hopefully there's no error. But, if any error occurs, it's usually a, 500 or 404. It's something predictable. It's something static. It's not necessarily dynamic in any nature. But with machine learning models, everything changes because that particular mathematical function evolves. Data can drift, prediction can differ, and if you are blindfolded, I know you have logs. Everybody has logs. I can see CPU, but it doesn't necessarily help me. Fuck the logs. I need performance. I need to see more output. I need to see stuff that models can give me. And usually right now about this stuff, I lost my words. Let's go on. Okay, the technical depth. So Google released a really nice paper in 2015 explaining the technical depth of machine learning models. What they actually explained here, they made a really simple parallel between classical software and machine learning. Package dependencies, like if you import some dependency and you call a function, that's also a fixed static import, right? And usually in machine learning systems, you have data, which is the lifeblood of your system, right? Nothing is built without data, right? Yeah, this was the first parallel, and the other was, by errors. So usually, in software we have runtime errors. Okay, so it will break my software, but some things can still run, hopefully. But machine models are usually blind. So you successfully shipped that model into production, and you run inference over it, and it works. Suddenly, your accuracy decreases after some weeks, a month. So you have 94%. It goes down to 63%, and you're like, shit. What are the investors gonna say? So yeah, and it works. But those are another type of errors, not necessarily code errors. Yeah, so that was the parallel. Going on, our own story. So I'll put the diagram here. This was our first diagram. I built it myself, and I still hate myself of not knowing all the cool software that we had. So we finally did it. We built the model. We built it. We reached 93% accuracy in tests, not necessarily in real cases. We launched it into production. All good. Thanks. First 3 months were amazing. We launched in 5 hospitals. It was really amazing. I had to do VPN access with like a bastion in all these hospitals, analyzing data and stuff at first. Because we had to know outputs and stuff like that. but more patients started to come. Scary. And then accuracy obviously started to decrease. Data started drifting because we trained our model on 10,000, 20,000 CT scans. But you trained your model on a set of features, historical data, and the real-time inference. When you are running online inference, you receive other types of data, right? So that can create a data drift and prediction drift between how the output changes. So yeah, that was our first system. That's beautiful, isn't it? Really amazing and simple. So what we did, because medical premises and hospitals don't necessarily let you sending around software and flying around software everywhere. They have rules, so they didn't necessarily let us to share a lot of things between us and communicate. So we had to somehow, the first rule was like, you cannot get data out if you don't anonymize that. So if you have, an ID of a user, you cannot send that data outside of the premises, right? So what we did, our competition, we did a really revolutionary thing like the French people did. We never changed the constitution like they did with cloud. They successfully forced their government to accept cloud, on-cloud infrastructure, which was against their constitution for medical environments. We didn't do that, but our competition usually shipped these things in large workspaces, computers, deploying that in the premise, no contact, no nothing. They had to go different trips, to different cities by car. I'm lazy, man. I don't want to go by car in different cities, put my stick inside the computer, analyze stuff. No, that's not for me. But what we did, I took a Raspberry Pi. That's, if you don't know about CT scans, usually we have PAX servers, and we have the DICOM protocol, which is the protocol they use to communicate CTs. What I did was, cool, let's use a Raspberry Pi. I got on the phone with everybody who had, firewall access, router access, stuff like that, and I told them, can you give me an IP? Sure, cool, that's everything I need, and a firewall, and I will give you the ports which you allowed me to contact you. That's cool. So what we did first was we executed, anonymizing stuff in the Raspberry Pi, and we had to send the CT scans inside our cloud environment, anonymized, obviously. So what we did was, actually, we thought of sending them using cache systems, but they were pretty large. So what we did was using store and forward, yeah, that design pattern. So we ship the links, basically. We actually upload the links inside our S3, and we ship the links to our RabbitMQ, to our network load balancer. And our RabbitMQ triggered inferences over Lambda. We never did inference on GPU. Everybody can do it. I dare you do it on CPU. Everybody can do inference on GPU. We trained the model and we did it on CPU, which was, I'm starting crying because it was a really nice adventure. Yeah, we did it. I mean, a lot of people don't know how to do inference on CPU, so we had an amazing team back then which helped us to do this amazing stuff. But at least I had, logs in CloudWatch and stuff. And yeah, we sent the artist struct, which is the output of the model, inside back into Raspberry Pi. And then the doctors had it available. We used some open source front-end tool so they can view, the contouring of the organs. So they had it, and they confirmed us that it was pretty good. So we were proud of us. After the party, and stuff like that, we started, bringing, sitting at the table, and we were like, this is not working necessarily. Okay, we had stuff, accuracy, decreased, but we really need to implement something more mature because, we had a lot of patients to take care of. So yeah, we basically started MLOps before it was mainstream and cool and sexy and everybody talking about it on LinkedIn. People who are AI influencers. Nice. Fucking dudes. Okay, so truth. Your model is 5% of your infrastructure. Your model is 5% of the system. That's the only part of it. That's why MLOps, it's not necessarily just ML stuff, you know. It's data engineering, it's software engineering, and it's ML. But mostly it's data engineering and software engineering. That's why projects like this fail. Because, you know, the ML guys, they were like, you know, math guys, researcher guys, which is cool. We have our own jobs. But they needed software guys and DevOps guys who can help them build something more mature. And everybody started, you know, sharing knowledge. And this is what they got to. So this is the ML model, but we have, you know, things like data engineering, I mean, feature extraction, yeah. Serving infrastructure. We did it on Lambda because we were poor. So somebody who is, you know, an experienced DevOps engineer can really know that we were poor. We were using Lambdas, you know, S3 and, you know, RabbitMQ and stuff. We didn't have a lot of money, so we managed to do it. I mean, yeah. So, pretty good. Let's go. Nice. The pillars of MLOps. This was the start of our journey, and didn't end up well because we don't have this. We don't necessarily have the startup right now. I mean, we failed, but we learned a lot. Business as usual. But these things really helped us. I mean, these things really helped us to build a more production system, more mature, robust production system. And if you ask me, machine learning systems, like any other system, have some, you know, non-functional requirements. First, they need to be reliable. It needs to work. You know, that inference needs to run. That prediction needs to be it. It needs to be performant. Everybody wants real-time models. You won't get it. Only with Edge AI. I'll talk about that shit later at the end of the presentation. Scalable, but not in terms of, you know, how many proxy servers, HTTP servers, whatever you put, in terms of how many models you can scale up and put so you can test. Usually when people, you know, are serving models in production, they're using a method called A/B testing. So what they necessarily do, they want to ship a new model trained on new features. And they still want to use, you know, the previous model because it's running and people are, you know, in the hospital and, you know, doing treatments. So they want to test their new model, and what they do is, you know, they're sending. Oh shit! No worries. No worries. I can help you. Should we stop? No? Okay. We'll leave it like that. Oh. So what they are doing is they are shipping another model, and they are sending 20% of their request to that particular model, so they can validate and evaluate that model if something works. You know, if the prediction is really okay, and we, you know, got the training right. After they prove that, yeah, certainly it works, they switch the models. That's the main idea. Yeah, because we need to maintain the functionality and the integrity of the system while, you know, people are on site. Good. So I built many diagrams for this, and this is actually our journey, how we introduce things inside our system. So first, version everything, not necessarily code. So code, everybody knows how to version code. Everybody's known Git and GitHub and GitLab. It's about data, and it's about models, and it's about configuration. Version everything, because if some of your colleagues would want, you know, to use the March 1971 data, which they built 3 months ago, 6 months ago, and they don't necessarily know what was that about, you would love to have data version. So they would love to have, you know, a way to reproduce the model with the exact configuration so they can debug it. hyperparameters, configuration, so version everything. What we did, we started with the data, because the data is the most important thing right now. So things evolved. Yeah, we used. There are a lot of tools to do data versioning. DVC, MLflow. We used LakeFS. I still don't know why. I didn't like DVC. I didn't understand DVC. It was some, Git for data, but we used LakeFS. So what we did here was we still had the training machine, and our colleagues still executed the training scripts manually on the training machine, which is perfectly normal, right? Yeah, we broke our S3 bucket in 3 different buckets because our landing zone bucket had to be configured for in a multi-tenant way because we had different hospitals, and I had to distinguish and store this data secure enough. I had to have some logical segregation of this data so I can distinguish between them. The landing zone was the place where we store the CTs. I explained you already. We have the training data bucket, which we use, LakeFS. So I somehow added an application load balancer so my colleagues could, go on the dashboard and, doing versioning my data set. And also for, GitHub, because we had a pipeline which transformed the CT scans we received so we could have versioning those data somehow. So I built our first automated MLOps pipeline for data versioning, fancy word. Nobody's using that stuff. I mean, there are a few people who are really implementing pipelines for training and data versioning and stuff like that, just a few. And these few people are the ones that I mentioned earlier, Amazon, the big sharks. You heard them. You heard about them. So then we had our model separated because we had to prepare for the model registry, which I will talk about in a few seconds. We uploaded the model right there. We still had the inference serving on Lambda, which now if I think about it, I was pretty stupid about the cold start. That really gave us a hard time. We used it was 300 megabytes model. It wasn't 7 gigabytes of a model 7 billion models right now have. We used a pretty small one, but also we could have done it better. So yeah. Model registry, cool. Love it. It was my idea that the new Docker registry, because it's the same, but not for Docker. It's for models, really. Now, you would ask me, why should I, create a central hub, central storage space where I can version my model and store it there? I don't know, because you may want to roll back, right? If you deploy your new model, even if your evaluation succeeded, things can fail, and you may want to roll back, and you may want to make experiments on it again. You may want to know, okay, who trained you? Which hyperparameter were used? Are you done? Is this model done? Who is the owner of this model? Things like this, just like in Docker, who created that Docker image? What was the status of that? I can use a Docker image to roll back if I use an orchestrator like ECS, EKS, and stuff like that. And we wanted to do that with our own models. We wanted to play it smart. So another version, pretty the same stuff, I see. The only thing we added here, a new ECS Fargate service with an MLflow. Somebody knows MLflow? So MLflow is a model registry, open source software. It's for storing models. All it takes is, an RDS for, a Postgres for having its own database, and a model, a storage space, an S-tray compatible or other file system storage space. So we can send the model in and creating a versioning layer over it, so I can usually have access on it. And now, instead of what is my inference function? Oh, here, nice. Oh, I forgot about that. Okay, so now the thing was, we, instead of getting our model from the bucket, we got our model from the model registry. Nice, and now I can roll back. I can, get any model I want from any version, stored, sealed. Everything is cool, so I don't lose stuff which I worked on. Not me, my colleagues, which my colleagues worked on, weeks and months to produce. And they may want to reproduce it, and they may want to version it. That's why we use this. And now the inference function, still doing the same stuff, but now we have a central place where we don't lose our models. Complicated? No? Right? Okay. Just wanted to check the temperature again. It's pretty hot in here, right? No? It's hot as fuck. Good. So, feature stores. What are feature stores? Feature stores are, features which you use to train models with, like characteristics about, information that you use to build your training data set. Feature stores solve. Remember that I said that AI systems need to be reproducible. So because you have the MLOps team, DevOps team, the engineers, and the ML guys who all collaborate under the same project. So we need to enable them so everybody can reproduce it. Even the new colleagues. Why should I, force them to have a 1 week onboarding, 2 week onboarding, and they don't get any stuff done? So they can have already a pretty perfect environment they can, experience and experiment model training. Yeah, that's what feature stores solved, and model registries and stuff like that. Reusability and reproduce. I could reproduce it and reuse it, because we build our features once and used in many places. So that's the main idea of feature stores. And yeah, really, it's about data governance, blah blah, a lot of security stuff everybody's talking about. Or did I still stalled by the CIA? So I'm playing skeptical. Sorry, excuse myself. Yeah. So things change again. Let's see. Oh yeah, this little friend got here, the feature bucket. We used Fist, but there are a lot of feature stores right now on the market. That was, the best open source solution we used. Fist was really, it was really good for us. It served us well at that time. And what we did to enable the data scientists and data analysts to use and to navigate and aggregate a lot of historical data so they can analyze it and can see. We stored the data in column-based database in Redshift. So we can give them, we computed the features, we stored the data inside Redshift. So any data analyst who had, the brains to analyze a lot of data could do it and access it anytime. Yeah. This is the feature store. So right now, instead of taking our features and our data and computing our features directly from our data bucket, training data bucket, we switched it, and the training server now loads automatically the features from the feature store. Yeah, because another advantage I would say it would be that people can, with these features stored in one single place, computed, you don't have to repeat the same operation all and over again. You can have the features right there computed. Anybody can reproduce any model behind. Is this the whole diagram? Yeah, the same stuff. Good. I think the next one. Oh yeah, this is the final system. This is it. I mean, it's not the end of the presentation. Don't worry. I'm here all night. This is the final diagram of the system. It's about monitoring. I don't know why we didn't implement monitoring in the first place, because the biggest problem for us was prediction drifting and data drifting, and I don't know why we didn't implement this in the first place. We started with we were human beings and we wanted our colleagues to have a really nice playing and experimental environment, not running playbooks on a server or Python scripts or training scripts on one server. So we gave them a pretty cool staging and development environment so they can play and they can create more models, because at the time we think we did it for head and neck and liver, I think, and we started experiencing extending the model to compute for other parts of the body. So they really needed to have separate environments and segregation and feature store and stuff. So yeah, monitoring. But wait, haven't we talked about monitoring in the first few panels? Right, but that's classical software monitoring, logs, CPU, as I told you. Here is more about problems that really appear if you are blindfolded and you cannot see from the output of the model. So you really want to see how data drift shifted from what we knew in what we had in the feature store and what we receive right now, and how different is the output of the inference serving and between the models, and periodically we wanted to see the output, what differs. And I was sick of logging in all these servers. I told you before, I'm lazy. I didn't want to go in hospitals and put my stick into the computer and start working and losing a lot of hours. I created myself a central VPN bastion server where I could connect to every hospital from any location. But still, I had to, without this thing, I had to go and still access and oversee data, stuff like that. So logs, classical logs and software logs weren't enough for us. We wanted to see more. We wanted also to measure model performance, so we see how much it takes to compute that inference. 1 second, 1 minute, 1 hour, 2 days. That's why we usually make this stuff. As I said, this presentation is more about awareness of the amazing things. I mean, this is still all software. There are way new solutions and products and open source stuff. If you want to use, if you don't want to, spend a lot of money to use. MLflow was the pioneer of model registry behind. FIST was pretty new. DVC was also, LakeFS was pretty new, but yeah, DVC was the oldest one. But right now, there's crazy software outside, which really, makes my life much easier. Because the more important thing is, productivity, right? I don't want to spend hours, days, weeks in using my environment. I want to have something which is stable and robust and scalable, and have fast access. Good. So how this thing changed? Oh yeah, I've explained you that. This. Oh, and also cool stuff. We changed Lambda, so we didn't use serverless functions anymore. We switched it to Fast API, but that wasn't enough either, and I will explain you why batch inference serving isn't for Fast API. There are a lot of inference Python frameworks that really do the job. But before that, I had my Bastion VPN instance because nobody inside my team had to access the logs and metrics from Grafana. So I used Prometheus. Using Prometheus was one thing that also forced me to use Fast API because Prometheus, as I know, has pull systems, so it pulls metrics from Fast API directly, and I provided an API for that. So I got my metrics from Fast API. Instead of Lambda, I really needed more power because I think at that time Lambda didn't have 6 virtual CPUs and 10 gigs of memory, or maybe they had, I don't know, or maybe our account was blocked to 3,000 megabytes, 3 gigs, sorry. Yeah. And what we did using Prometheus, we took the matrices from Fast API to Prometheus. We shipped them in Grafana. I gave them a WireGuard server so they can always go and access them, and that was the job. And replacing Lambda with an EC2 infrastructure with ECS so I can scale better. But instead of using Fast API, some cool stuff really appeared in the recent years, excuse me. Like, anybody heard of Bento ML? No? Ray.io? Okay. Litserv? No? Man, I need to send you some really amazing stuff. Links, documents, everything. So what these guys did, because I had to load my model on the inference server, which was pretty fine, but I had to load it every time. And I was like, okay, cool. I will just span more workers. Go Fast API, UV core, span more workers. That should do the job. Replicating more Fast API instances and stuff like that. And I was like, man, this costs a lot of money because of that model. So what we did, we found out, this frameworks, which what they did was, separating the model storage from the HTTP serving. So they created a layer of HTTP, which they created the 2 different scalable units, layers which scale differently. They had an HTTP server, which it concerns with HTTP stuff, with web stuff, and they separated down a different infrastructure of workers, a shared pool of workers where they can load the model once and run batch inference over them. Because with Fast API we had to load the model, and somebody had to do they sent files and we had to do inference, and we only had we used like 5% of the cluster when we ran that inference on the models, and we were like, man, shouldn't we use the whole cluster? Shouldn't we use the whole cluster power? And they were like, yeah. And we found out these frameworks, and these frameworks help me distribute my inference over many workers which have a shared pool of of computation. They are shared among the workers. So yeah, that was it. Oh, pipelines. Do you want to talk about pipelines? I mean, startups don't necessarily do pipelines in MLOps. We still use basic CI/CD, the old stuff. I mean, data pipelines are cool. Yeah, ETL pipelines, sure, but it wasn't our case. I mean, we had CT scans. We didn't have to do any ETL processes over CT scans. Maybe if you have medical patient data from medical sheets, extracted from an OCR, that's another stuff. Yeah, you should do data validation over that with strict contracts. Training pipelines, yeah, it would be nice to but we didn't have a GPU infrastructure. We still had our old workspace where we used to train our models in. If I had a GPU infrastructure really complicated, and I had to run automatic training, when inference has been done and collected a few features. So if I've seen that accuracy dropped or I had data drifts, yeah, I could have triggered the new model. That's okay. Validation pipelines, yeah. I just don't know. Startups are not using this stuff because it decreases productivity. It decreases your way to production. Which takes me to the next slide. Which should you use MLOps first? I mean, should you implement MLOps at all? I mean, I gave you a shit talk about MLOps, for like 30 minutes, and should we use it, MLOps? I mean, should you? Yeah, maybe you should, but not in the beginning. I still have the curse of, trying to make things perfect from the start, instead of, writing just a small piece of code, like a garbage, and garbage, and trying to build from that point on. I mean, everybody does. Everybody wants to write the perfect software or the perfect model. There isn't any. This is a fairy tale told in university, so you can believe that you can do it, but you can't do it. But you can be. You can do it next day. Next day you can be better than you were before. So your software can be better if you do the factoring, you apply design patterns and stuff like that. But yeah, MLOps. I mean, MLOps is cool and amazing if you reach maturity to your product, or if you build a service for a client. Yeah, if you reached maturity, you have a clear hierarchy of people. Like if you have multiple guys in your team, data engineers, data analysts, ML engineers, feature engineers, all these roles, man. Software engineers and stuff like that. Yeah, it's worth of using MLOps, and you should do it. But in the starting point, from where your software lives, no, you should be more concerned with building that model, shipping it, and yeah. I have 3 minutes left. Oh man, I have a lot of spicy stuff. So LLM ops, 3 minutes, good. So what LLM ops did, instead of model versioning, we had prompt versioning. Everybody knows what's a prompt, right? You use it every day. Cool. So we had to model prompt. We had to version prompts because we had to go back in time and see why the output of the LLM is wrong by applying the particular prompt. A training pipeline got ingestion and indexing pipeline. So I'll explain it to you in the other diagram. I cannot explain it right now. It's pretty different stuff. Model evaluation, LLM evaluation, anytime. So if you build prompts and you have outputs, you want to evaluate if that particular LLM, gave what you had to receive, like it worked in a reliable way. Just like model evaluation. Feature stores, now it's context management. Context management, agents, everybody does agents right now, but few people really know about the underlying problems of agents, which are, memory management and context management, which, if you give 10 agents access to the same memory location, oh God, they can, inject context from different memory, and they can really create noise and hallucinations. And about this stuff, nobody talks about LinkedIn in this stuff. This stuff is we learned it the hard way. And that's why, we created a newsletter, and I will give you the newsletter if you want to check out the cool articles we are building, similar stuff which I presented to you here. Model monitoring, LLM monitoring, all the time. So LangFuse, if anybody knows LangFuse. Nice, you don't count, you're in my team. LangFuse, you really want to see the underlying process of how your LLM performed, like how many tokens it got you, how many time it took to execute the prompt, literally any information you can observe, and understand why the hell it cost $1,000 for one single call. That's why we use LLM observability, really. Good. This is a rack system, which we recently did. I cannot disclose the name of the client, really, but we built this stuff for them. I can explain it to you, and I can send it to you because Luci is giving me a hard time. So if you want me to explain it, what it is, we can stay, a bit late behind, and I can present it to you. It's about, that's the ingestion and indexing pipeline. Taking documents, OCR them, do structural modeling over it. So taking a structured data and structure it. You know why rack system fail right now? everybody's treating rack system from LLM point of view, not from data point of view. Data modeling really does the job, right? Instead of, using and changing models, you should, model your data so you can first hit your vector database with the correct data, metadata, instead of using, and adding more embeddings. Really, I can explain you this cool stuff, why we use multiple vector embeddings behind, but afterwards. Oh man, good. Next, okay, give me 2 minutes. I'm really interested in this subject, would you please, man? Thank you. So Edge, the next stuff. Good. So we had some requests of models that can run on your local phone. Nobody talked about that, right? So yeah, we had some requests. SLMs, which does specialized things. Man, the clients really kill us with research. So we started analyzing this Edge initiative, which a lot of people, right now is considering Edge to be, federated learning and distributed inference. It's not about that. It's about, deploying LLM, STT, or whatever models you want on a Raspberry Pi, on a phone, on an FP, on FPGA, on any microcontroller and stuff. But we have certain limitations, right? We have memory limitations, we have power limitations, power consumption limitations. We even have what was that? Forgot. Yeah, whatever. In the case for privacy, because they wanted privacy, they ran like kind of a WhatsApp or Signal for governmental stuff. So they wanted LLM enhanced functionality inside their own premises. Summarizing, a video and call understanding and transcripts directly from their own phones and stuff like that was hard. Even fine-tuning this in different languages was hard. Arabic language gave us a really hard time, and Chinese. Oh man, you cannot fine-tune this stuff in Chinese. So yeah, currently this is if you take all the case studies which are published right now, if Edge, this is the next movement. Dev Edge Ops tools already started adapting. Docker, Kubernetes started adapting themselves to deploy stuff on Edge. So why wouldn't you? Something I've missed a lot. I mean, I forgot almost half of the text I prepared for this session, and most of it was done, freestyle. Sorry for that. I really got nervous, and I started, shitting my mouth around, about this stuff. Sorry for talking too fast. I know I do that. I really apologize, and really thank you so much for giving me the chance to present you this stuff that we did. I really hope this was educational for you, in the sense that you really learned something and you really wanted to explore more about these things, because these things really matter. If you want to keep your job, obviously, I mean, in the next years, if nobody adapts or use this kind of stuff, the existence of our jobs would be that. So yeah, good. Thank you so much.
Questions?
Oh man. Okay.
You got 5 minutes for questions. If there are any questions, let's see.
Please. Questions. Yes.
So with this all agentic and as LLM enters out into our work field, do you imagine or would you like that AI would be an ecosystem and you just plug into it? I saw the diagram from others. Would you like an ecosystem like AI as an operating system? It's often.
Wait,
would you like something?
Let me come there, because I had a hard time hearing you. So let me.
Would you like AI as an operating system? Because I saw that the diagrams to connect things there, and that's separate. Like the project, database account, would you like an AI as an operating system? Would you like this?
Are you trying to sell me some stuff? Oh man, you're trying to sell? You're building some product? You want to sell me some stuff?
Not with AI operating
Afterwards.
system, but-
I know you have the cool shit. So yeah, AI agent, no, I wouldn't want that. Or at least I don't necessarily know because I haven't explored that yet. So I don't really know what's that about, agentic OS systems, stuff like that. I use Cursor. That's enough for me. And I have an army of junior AI agents that will help me with shit I don't want to get done. So they figure it out. Other questions? Please.
What happened with the first project, the one with CTAs?
What happened?
Yeah, what happened?
Man, the startup died. We still have jobs.
Did you make it open source somewhere, or
Please, again?
did you make it open source, the models at least?
No. No. It's based on real patient data. I signed, we signed, not necessarily me, the CEO signed
I mean,
some really
the
bad
models.
NDAs. What?
I mean the models.
No.
Just the data, just the models.
No. Powerful NDAs. Cannot do it. Next question. Sorry, man. No, I don't want to, get in trouble. Really. Other questions? Or I would take silence as a no. And I will leave you to go eat some pizza, drink some beer, get drunk, whatever.
Okay,
Bye. Thank you. Sorry.
Okay, before we go to the pizza, which is across the hall, I just want to let you know that, and remember, we have two big events in Romania for the Cloud Native Days in May, 18th and 19th of May, and also in Timisoara, 23rd and 24th of April is AWS Community Day. So watch out for these events, and let's go for pizzas. Thank you for coming.
It was originally no, another one, because originally